In this series of lectures, starting with blackbody radiation, we are going to discuss the foundations of quantum mechanics. The strange, bizarre, and yet wonderful journey of quantum mechanics begins with the famous invention of Thomas Alva Edison, electric light bulb. This humble electric bulb captivated the research interest of the scientific world, and the failure to explain the nature of radiations emitted from a particular type of bodies called black bodies by the existing science and technology, the classical and electrodynamics, forced the scientists to think differently, and the seed of quantum mechanics was shown. If we consider a light bulb, where it is just switched on and a small amount of electricity passes through it, we may not observe any light coming out of it. But if we place our hands near to the bulb, we can feel the heat of radiation as the infrared radiation is emitted from that bulb. As more electricity passes and temperature rises, the electromagnetic wave may enter into the visible spectrum, and reddish light emitted from the bulb might be observed. Now, with more electricity, more temperature, the light bulb may emit, say, orange light, and with more increase in electricity, that is, if we increase the temperature of the filament, then the color of that bulb will may change from red to orange to yellow now. Now, if we increase the electricity to a high extent, then instead of yellow, we may get yellowish white light coming out of that bulb. But whatever amount of electricity enters into that filament, we never get the uh, maximum frequency or minimum wavelength in the visible range, that is blue or violet color. Why blue is so hard to get? To answer that question, the scientists heated a particular type of bodies, black bodies, and observed the intensity or emissive spectrum for those bodies at different temperatures. In order to understand black bodies, we need some other definitions, like the emissive power of a body kept at a certain temperature is the amount of energy radiated normally from the body per unit area per unit time for a particular range of wavelength. That is, if we consider a body and when the body is heated at a particular temperature, then it emits radiation in all possible directions. The amount of energy radiated by the body normally per unit area per unit time is called the emissive power of that body at that temperature for a particular range of wavelength. On the other hand, the absorptive power of a body kept at the certain temperature is just the ratio of the energy absorbed by the body to the total energy incident on it. Therefore, if Q be the amount of energy incident on the body and Q dash is the amount of energy absorbed by the body, then the ratio of Q dash to Q is the absorptive power, or in simple words, the absorption coefficient of the body. And when the body is unable to absorb any part of the energy incident on it, that is Q dash is 0, then it has the lowest possible absorption coefficient, A lambda 0. On the other hand, if the body can absorb the whole amount of energy incident on it, that is Q dash equals to Q, then the absorptive power of the body is maximum, that is 1. Therefore, the range of absorptive power is 0 to 1. When absorptive power of the body is unity, that means whatever amount of energy is incident on the body is completely absorbed by the body, is called black body. So an ideal black body is a body which is capable of absorbing the whole radiant energy incident on it without any part reflected or transmitted. Therefore, ideally, a black body has the absorptive power of unity. Although a perfect black body is an ideal concept, practically lamp black and platinum black can serve the purpose of a black body. In fact, practically we can make black bodies like Ferris black body can be prepared. In Ferris black body, a double-walled sphere is used with a small orifice through which the incident radiation can enter into the body. The space between the two walls of that hollow sphere is evacuated to prevent heat loss by the way of conduction or convection. A small conical projection is placed just the opposite to the orifice to avoid direct reflection. And the inner wall of that hollow sphere is coated with lamp black or platinum black, having very high absorption coefficient. So when any radiation enters through the orifice and incident on a part of that wall, then maximum amount of radiant energy is absorbed by the lamp black present at that portion, and is very small portion is actually reflected. And when that reflected light is incident on any other part of that wall, then again maximum energy will be absorbed and a small part will be reflected. And the process will continue until the whole amount of energy will be absorbed by that body. Therefore, if an observer is watching the process from outside, for that observer, whatever amount of radiation is incident on that Ferris black body through this orifice, it never comes back. Therefore, for that observer, it acts as a perfect black body. The whole amount of energy is completely absorbed by that body. No part of the incident radiant energy is reflected or transmitted by that body. Therefore, practically, a black body has very large absorption coefficient, and that value is nearly unity. Now, according to Kirchhoff's law of radiation, the ratio of emissive power to the absorptive power of a body at a certain temperature is always constant. That is, mathematically, E lambda by A lambda is constant. Therefore, if we have a number of bodies, 1, 2, 3, etc., having different emissive and absorptive power, and all are kept at a certain temperature, all are kept at a fixed temperature, then say E lambda 1 and A lambda 1 are the emissive and absorptive power of first body, E lambda 2, A lambda 2 are those of the second body, E lambda 3 and A lambda 3 are emissive and absorptive power respectively for the third body, and so on. Then the ratio of this emissive to absorptive power is constant. So this value is constant. So if one of these bodies is a black body, that means which is capable of absorbing the whole amount of incident radiation, then we can say the capital E lambda to capital A lambda for that black body is also constant. Now, since the ratio is constant, if A lambda is somehow increased, then E lambda should also be increased so that their ratio remains constant. So, if a body has high amount of absorption coefficient, A lambda is very high, then according to Kirchhoff's law of radiation, the E lambda of the body, the emissive power of the body, must also be very high. Therefore, a good emitter is also a good absorber, or a good absorber is also a good emitter. Since in case of black body, we know that absorptive power or absorption coefficient of a black body is close to unity, the maximum possible value for absorption coefficient, the E lambda, that is emissive power of the black body, is also very high. And since the emissive power of a black body is very high, that is when a black body is heated to a certain temperature, then it is capable of emitting a high amount of radiant energy. This type of bodies are used by the scientists to experimentally observe the intensity of emissive spectrum for different temperatures. And if we look into the intensity spectrum of a black body kept at a temperature T1, say at 1000 Kelvin, then we observe that the intensity, that is the amount of energy emitted by the black body per unit area per unit time, intensity as defined as the amount of energy emitted by a black body per unit area per unit time, is not uniformly distributed among all the wavelengths. The intensity of radiation is not uniformly distributed among all the wavelengths. The intensity increases with increasing wavelength, attains a maximum at a certain wavelength, say lambda m1 for temperature T1, and then decreases monotonically with increasing wavelength. If temperature is increased, that means if that black body is heated to a higher temperature, say T2, say T2 is 2000 Kelvin, then as we are supplying more amount of heat energy to the body, it is expected that we should get a larger amount of radiant energy, and that's what is observed here. The intensity of radiation for all wavelengths increases. And again, intensity is not uniformly distributed among all the wavelengths. Rather, intensity increases with increasing wavelength, becomes maximum at a certain value of wavelength, and then decreases with increasing wavelength. Another point is to be noted here is that whenever the temperature is increased, the wavelength corresponding to maximum intensity now is shifted towards the lower wavelength side. The peak, the intensity peak is now shifted towards the lower wavelength side as the temperature is increased. So if we again take the example of the light bulb, for a particular temperature, say we are observing reddish light emitted from that bulb. Now when the temperature of that bulb is increased, temperature of the filament is increased by passing more amount of electricity to it, then the total intensity emitted by the bulb is increased, and at the same time it is observed that the wavelength corresponding to the maximum intensity is now shifted towards the lower wavelength side. So we may observe the orange color of light coming out of that bulb instead of red now. If the temperature of the black body is increased more, say now the temperature is increased to T3, say 3000 Kelvin, again we observe similar pattern. The intensity increases with increasing wavelength, becomes maximum at a certain wavelength, and then decreases with increasing wavelength. And again we observe that as the temperature is increased, the wavelength corresponding to the maximum intensity is now shifted towards the lower wavelength side. So as the temperature is increased, the wavelength corresponding to maximum intensity shifts towards the lower wavelength side. When observed it experimentally for different types of black bodies kept at different temperatures, and in all cases it was experimentally verified that the peak always displaced towards the lower wavelength side when temperature is increased. So lambda m, the peak, the wavelength corresponding to the maximum intensity, is always inversely proportional to the temperature. That is, lambda m T is constant, and that constant value is 2.9 into 10 to the power minus 3 meter Kelvin. And this law is called Wien's displacement law, which says that when the temperature is increased, then the peak is displaced towards the lower wavelength side, such that the wavelength corresponding to maximum intensity is inversely proportional to the temperature. Or in other words, lambda mt is constant. So if we heat a black body at a certain temperature, and if it is possible to estimate the wavelength corresponding to the maximum intensity of light coming out of that body, then from this Wien's displacement law, we can estimate the temperature of that body. Now again, if we observe the intensity of radiation at the smaller temperature T1, this will be the nature of the intensity spectrum. So here, this curve tells us that we can have different values of intensity for different wavelengths, such as for this particular wavelength, the intensity is this. For the wavelength this, the intensity will be this, and so and so. So for each wavelength, we can estimate the intensity of radiation. Now, if we are asked what is the total intensity of radiation, that is what is the intensity of radiation for all wavelengths, then we need to think of the intensity for each and every wavelength and then add them, which is nothing but the total area under this curve. So this is the total, this shaded region is the total intensity of radiation for all wavelengths when the body is kept at temperature T1. So if we increase the temperature of the body, that means if the black body is now heated to higher temperature T2, then intensity spectrum will look like this. And then the total intensity of radiation, for all wavelengths will be the area under this curve. So this is the total intensity of radiation. And if the process continues for any higher temperature, like say temperature is now increased to T3, then total intensity of radiation for all wavelengths will be the area under this curve. So when the temperature is increased, then the total intensity for all wavelengths is enhanced drastically. And Stephen and Boltzmann experimentally observed that this total intensity of radiation for all wavelengths depends only on the temperature at which the body is heated. And according to Stephen Boltzmann law, the total intensity of radiation for all wavelengths can be estimated from the area under the curve. That is, if we take the integration for all wavelengths, then E will be proportional to, fourth power of temperature at which the body is heated. Therefore, E equals to sigma T to the power 4. And sigma is a constant and is called Stephen constant. The value will be 5.67 into 10 to the power minus 8 SI unit. Therefore, according to Stephen Boltzmann law, the total intensity of radiation depends only on the temperature of that body, and it is fourth power of the temperature of the body, and that's why when the temperature is increased from T1 to T2 to T3, the intensity of radiation is increased drastically. So, in summary, the energy coming out of the black body is not uniformly distributed throughout the spectrum at a particular temperature. Rather, intensity of radiation increases with increase in temperature for all wavelengths, and at a particular temperature, the intensity of radiation increases with wavelength, becomes maximum at a certain value of wavelength, and then decreases with increasing wavelength. The wavelength corresponding to the maximum intensity shifts towards the lower wavelength side when the temperature is increased. So that if lambda m corresponds to the wavelength for which intensity is maximum, then lambda m is always inversely proportional to the temperature. In other words, lambda mt is constant. And this is called Wien's displacement law. So according to Wien's displacement law, when the temperature of the black body is increased, the peak of intensity always shifts towards the lower wavelength side. Or in terms of frequency, the peak shifts towards the higher frequency side. The total intensity of radiation at a given temperature can be estimated by the total area under the curve, and it is found to be proportional to the fourth power of temperature. That is, if I say total intensity of radiation for all wavelengths is E, then E is proportional to T to the power 4. T is kept in Kelvin, and we call it as Stephen Boltzmann law. So if we try to do some numericals with these two formulas, we have, say, an electric heater emits 1500 watt of thermal radiation. Assuming the coil of the heater radiates like black body, determine its temperature. The surface area of the coil is given as 0.03 meter square. And there is only one law which corresponds to the total intensity of radiation with temperature, is the Stephen-Boltzmann law. Now, according to Stephen-Boltzmann law, the total intensity of radiation E equals to sigma T to the power 4. Now, as per the question, instead of the total intensity of radiation, power is supplied. So here 1500 watt is the power supplied. Now, how do we define intensity of radiation? Intensity is defined as the energy. Intensity is defined as the energy per unit area per unit time. But you know, energy per unit time is nothing but the power. So we can say intensity is power per unit area. Therefore, our Stephen-Boltzmann law, which is E equal to sigma T to the power 4, can be easily written as P equals to sigma to the power 4 into A. E equals to P by A, therefore P equals to E into A, and we know E equals to sigma to the power 4, so it is sigma T to the power 4 into A. Now here power is supplied, cross-sectional area is supplied. Sigma, the Stephen's constant, is known, 5.67 into 10 minus 4 SI unit. So we have to estimate the temperature from it. So if we write it in terms of temperature, it will be P by sigma A whole to the power 1/4. If we put the values, P as 1500 watt, sigma as this, and cross area as 0.03 meter square, then temperature is estimated to be 969.1 Kelvin. So temperature of the coil is this value if that coil is treated as a black body. Similarly, the second numerical, it says at what wavelength does a room temperature object emits the maximum thermal radiation? This is the first one. It says at what temperature does a room temperature object emits maximum thermal radiation? So as per the question, here we need to find out the temperature of that object which emits maximum thermal radiation. And we know in the Wien's displacement law, which tells us that lambda mt equals to constant. T is the temperature of the body, and lambda m is the wavelength corresponding to the maximum intensity of radiation. So we can use Wien's displacement law here. So here lambda m into T is constant, and the constant value is, as we have discussed before, is 2.9 into 10 minus 3 meter Kelvin. So temperature is given, so we need to just convert the temperature in Kelvin. So it needs to be converted into Kelvin, and if we convert it, it will be 307 Kelvin. So temperature is now known, constant is known, so I need to estimate lambda m, which will be of this value. So this is the wavelength of that emitted radiation when the body is kept at 34 degrees centigrade. Now in the second question it says, to what temperature must we heat it until its peak radiation is in the red region of the spectrum? So now we need to increase the temperature so that the wavelength is now shifted into red spectrum. That means the wavelength corresponding to the maximum intensity will be 650 nanometer. So again, we can use Wien's displacement law. Only in this case, wavelength corresponding to the maximum intensity is given, and we have to estimate the temperature. So same process, only we need to estimate the temperature, and the temperature comes out to be 4461.5 Kelvin. In the third part, it says how many times more thermal radiation will the body at higher temperature emits with respect to the one that at lower temperature. So now we need to find out the ratio of total thermal radiation of the body. So whenever we need to estimate the total thermal radiation, total intensity, then it will be Stephen-Boltzmann law. So according to Stephen-Boltzmann law, the total intensity of radiation is equal to sigma T to the power 4, where T is the temperature at which the body is heated. So in the first case, the temperature was T1 Kelvin, 307 Kelvin, and in the second case, the temperature T2 is 4461.5 Kelvin. Therefore, the total intensity of radiation for the first one will be sigma T1 to the power 4, while in the second case it will be sigma T2 to the power 4. Now we need to find out the ratio of E2 to E1. So that ratio will be sigma T2 by sigma T1 to the power 4, that is T2 by T1 to the power 4. If we put the values, we get E2 by E1 as 44604. So this amount of more thermal radiation the body at higher temperature will emit with respect to the body at lower temperature. Thank you.